A Machine with Short-Term, Episodic, and Semantic Memory Systems. It's written by Taewon Kim, Michael Coates, Vincent Francois Lavette, Mark Nierix, and Piet Vossen. We are located in the Netherlands, and I'm the presenter, Taewon Kim here. So this is the hierarchy of human memory system. So memory has short-term and long-term memory, and long-term memory consists of explicit and implicit. Explicit is something more that is explicit, more conscious. And this consists of episodic memory system and semantic memory system. So semantic memory has to do with the world general knowledge. For example, where are laptops usually located? And episodic memory has more to do with your personal memory. For example, where did I leave my laptop yesterday? And so how we think about it is that machines, AI, a lot of them are focused on semantic memory. You can Google it, you can ask GPT-3 about world general knowledge, and they will give you good answers. But they were not going to give you answers related to your personal memories. They're not designed for that. But imagine you want to have machines or AI around you, you want to ask personal questions. And then you want these machines, AIs, to have episodic memory system. So we're inspired by this idea, and then we wanted to experiment with this. We start with Discrete-event simulation. So in this simulation, there's a room with humans, objects, and possible object locations. Every human can place an object at one of the possible object locations within their capacity limit. Humans can place their objects on a common sense location, for example, a bowl on the cupboard, or a non-common sense location, a bowl in the wardrobe. We define common sense using ConceptNet here. So now we're going to talk about the room environment. It's a wrapper around the discrete event simulation we just talked about, and here in this environment, agent can only partially observe the entire state of the room. It cannot see all of the humans, all of the objects, all of the locations at the same time. It can only partially observe it, which encourages the agent to have a memory system. The agent observes one human at a time. For example, at time step 42, the agent observes that Alice has her laptop on her lap. After each observation, the agent is asked a question about the current state of the ES. Where is Alice's laptop? If it answers correctly, it gets a reward of +1, and if not, it gets a reward of 0. The observations made are given as quadruples, H, R, T, and timestamp. Here, H, R, and T stand for head, relation, and tail respectively. This means that the agent observes that the entity H has the relation R to the entity T at the given timestamp. For example, Bob's laptop at location desk, timestamp 42. The question is given as a triple, head, relation, and question mark, such as where is Bob's laptop? OpenAI Gym compatible and is open source at this address. Human-like memory systems of our agent. Now we have designed our environment, we have to design our agent that will interact with the environment to maximize its rewards by answering the questions. Every observation is initially stored in the short-term memory system. When it gets full, the agent must decide what to do with the oldest observation in the short-term memory. It can take one of the three actions. First, forget it completely. Second, move it to the episodic part of the long-term memory system. Third, move it to the semantic part of the long-term memory system. So as you can see from the right-hand side of this diagram, the oldest short-term memory, the agent has to decide if it wants to put in the episodic memory system, semantic, or just forget about it. So examples of the episodic and semantic memory stored. What are these memories stored in each memory system? These are some of the examples. So all of this memories stored in the episodic memory in each memory system are quadruples. Here is an example of episodic memory. Bob's laptop at location desk at timestamp 42, head, relation, tail, and the fourth term timestamp. Semantic memories is similar, head, relation, tail, and the fourth term is strengths, which has the value of 3. So there are two differences here between these two memories, is that episodic memory is more personal. So that's why if the agent has seen Bob's laptop, then it will remember that it's Bob's laptop. And it will also remember the agent has seen that at timestamp 42. As for the semantic memories, the memories are not concerned with individuality. It doesn't necessarily have to do with Bob's laptop, Alice's laptop whatsoever. It's just the laptops in general are generally located on the desk. And if the agent has seen this 3 times, then it will have strength value of 3. Each memory system has a list of quadruples. Each memory system is a knowledge graph. Memory storage policy. All three memory systems here, short-term, episodic, and semantic, are bounded in size. Each of them is a knowledge graph where the number of quadruples is limited. We use the cognitive science theory to manage the episodic and semantic memory systems. That is, if the episodic memory system is full, we forget the oldest memory stored. If the semantic memory system is full, we forget the weakest memory. Dealing with the short-term memory system when it is full is more interesting and challenging. We use reinforcement learning to learn this. More specifically, we use deep learning here, and it's open source at this address. Memory retrieval policy. In our scenario, each time an agent is asked a question, a relevant memory has to be retrieved from the knowledge graph to answer the question. If the environment asks the agent a question, where's Bob's laptop, then the agent has to retrieve relevant memory either from the episodic memory system or from the semantic memory system to answer this question. We handcrafted this policy. How we did it was first look up the episodic memory system to find the relevant memory. If there is, then use it to answer the given question. If agent has stored this relevant memory in its episodic memory system, then it will use this memory to answer the question. If there is no relevant memory stored in the episodic memory system, then look up the semantic memory system to answer the question. So if it cannot find anything about Bob's laptop in its episodic memory system, then it can look up its semantic memory system, something like laptop allocation task. The agent has seen something like this 3 times. So agent think that this is a general word knowledge, then it will use this general knowledge in its semantic memory system to answer the question. So there are 2 policies here, which I talked about, memory storage policy and memory retrieval policy. So what's happening here is that the better the agent manages its memory storage policy, then the more likely that this handcrafted memory retrieval policy will give you more rewards. So since we're using deep learning, we have to think about what the state looks like and what the actions look like. Let's look at the right-hand side here. This is the Q network diagram where the short-term memory MO, episodic memory ME, and semantic memory MS are given as the initial input. So each of these are knowledge graph, and each knowledge graph have to be converted to numeric values. So we're gonna convert them to knowledge graph embeddings representations, all 3 of them separately, and then each of them will go to LSTM block. After which comes multilayer perceptron. We're going to concatenate them, and it goes to another multilayer perceptron. And this multilayer perceptron at the end will output 3 values, which are the Q values of each action. So if we write this out into an equation, it will look something like this. This is the Q network. And so what is the knowledge graph embedding representation of memory systems? So like I said, each memory system is a knowledge graph. They have to be converted into numeric values. So this is the example of converting an episodic memory system into a knowledge graph embedding representation. So this is an episodic memory system of the agent. It has 3 memories: head, relation, tail, and the timestamps. And then we're going to order them by time. So this one comes first, and this one comes second, this one comes third. So after this, this is a list of ordered memories. So we can just remove the time values here in more compact form here. And each of the entity and relation, we're gonna convert it into we're gonna convert them to embeddings. This is Alice's phone. We're gonna add embedding of Alice and embedding of phone so the agent understand this is not just a phone, this is Alice's phone. After this, each memory here, we concatenate head, relation, and tail to make so that this one memory, each memory, gets converted into 1 numeric value. So now this knowledge graph in the beginning is converted into a list of vectors, which can be plugged into an LSTM now. Experimental setup. We're going to talk about some of the parameters here. The environment terminates after 128 steps, which means there are in total of 128 questions asked per episode. Total maximum rewards per episode is 128. The questions about object locations that the agent has observed are sampled uniformly at random. Experimental setup. We have come up with 5 different agents. First, reinforcement learning agent, semantic from scratch. So this one starts with an empty semantic memory system. Second, reinforcement learning agent, semantic pre-trained. It starts with general word knowledge from ConceptNet in a semantic memory system. It's already pre-filled with them. We want to investigate whether agents that know about the world would learn differently from those that start from scratch. And these 3 are the baselines, so we can compare it with the first 2 reinforcement learning agents. Random agent chooses one of the 3 actions uniformly at random. Episodic only agent only has an episodic memory system and always moves the short-term memory to it. Semantic only agent is similar, except that it only has semantic memory system and always moves the short-term memory to it. All of them have the same memory capacity to make a fair comparison. The size of short-term memory is 1 and long-term memory is 32. If it has 2 long-term memory systems, then each of them will be 16, and if it only has 1 long-term memory system, then it will have 32 memories stored in it. So these are the results. Here it shows the average loss, DQN, we use a temporal difference loss here, average loss of training, and here in the middle it shows average total rewards per episode in the validation environment setup, and here on the right hand side, these are the total rewards for the 5 different agents in the test environment. Here you can see that actually semantic memory system pre-filled agent is converging to lower loss value than the one start from scratch. In the validation setup, we see a similar thing where the semantic memory pre-filled agent is not only learning faster but also converging to a higher optimum, thus having more total rewards than the one start from scratch. And these are now comparing with the other 3 baselines: episodic only agent, semantic only agent, and random agent that takes one of the 3 actions at random. Of course, this has the lowest total rewards. And this light pink and the red pink are each of them are semantic from scratch and semantic pre-trained. So as you can see from here, reinforcement learning agent that has a semantic memory system pre-filled is learning faster and learning better. So that's nice. What are these agents actually learning? And then we looked into the Q values to see what the agents think, what actions are more value than the others given a state. So we noticed one same strategy between the 2 reinforcement learning agents. Both of them think it's more valuable to store a not so common short-term memory. For example, Frank's train at location circus timestamp 86 in the episodic memory system. But we observe one fundamental difference between them. Whenever the semantic scratch agent observes something that is generalizable, for example, Anne's bowl at location cupboard timestamp 2, it stores it in the semantic memory system, while the semantic pre-filled agent never decides to store any short-term memory in the semantic memory system. It always forgets generalizable short-term memories completely. This makes its semantic memory system untouched. As it is filled in the beginning, it stays the same until the end. What we observe is that it retains the general word knowledge it was given. This is comparable to a pre-trained neural network, so related work. So our work stands somewhere between cognitive architecture and machine learning with memory systems. Cognitive architectures focus on the theory of the human mind, while machine learning with memory systems try to take advantage of memory systems to solve problems such as partial observability and catastrophic forgetting. There are many other things. Please read our paper to see a more comprehensive literature review. In the future, what we want to do, we want to make our environment more complex. We want to include more relations in its triples, but also multimodal. The questions given by the environment can extend to a natural language with ambiguity, not just triples. We would also like to add other kinds of human memory system to our agent, for example, working memory, implicit memory, and etc. And we also want to see humans collaborating with agents with these memory systems. We would like to thank the Hybrid Intelligence Center funded by the Dutch Ministry of Education, Culture and Science in the Netherlands. Thank you.